right, well, thanks for joining us for May's edition of the SCAAS Journal Club. Tonight, instead of two papers, we're actually looking at a couple pages from Julio Magli's Archaeoastronomy, Intro to Science of Stones, which is designed as an undergrad introduction to archaeoastronomy, and William F. Romaine's Notes on the Accuracy of Google Earth Pro, Heading Information for Archaeoastronomy and Landscape Archaeology Studies from the journal Skyscape Archaeology. Actually, the current issue. It's a public access, one of the few articles, I believe, this edition. So we're going to be looking at Google Earth as a tool for archaeoastronomy for use, and let's just jump right in. So Magli's book dedicates just a few pages in discussing methodology on virtual globe software and its use in archaeoastronomy and gathering measurements. So a virtual globe, and this is pulled from Wikipedia, is a three-dimensional software model, a representation of Earth or another world. Google Earth Pro, for instance, has Mars and some other things to look at. Virtual globe provides the user with the ability to freely move around the virtual environment by changing the viewing angle and position. Compared to conventional globe, virtual globes have additional capability, representing many different views of the surface of the Earth. So I believe everybody's familiar with this from just playing around. We're going to look at a couple tools tonight that would be of interest to us in our archaeoastronomy studies. The benefits of using virtual globe are obvious. Some of the sites that we might be interested in are inaccessible due to hazardous conditions, conflicts, war, terrorism. I know Central America, where I go, there's more and more concern over kidnappings and things like that. More importantly, maybe travel costs, permit access, which we were just talking about, are just the time constraints of everything we have going on right now, which really opens up, more opportunity using some of these remote access tools. Another point that Magli makes is we can benefit using this because some of the visibility lines that were viewed by ancient people are obscured today by modern constructions and buildings. And this is a good way to recreate some of those lines of sight that are no longer visible. So the first virtual globe software that we're going to look at here is Google Earth Pro, abbreviated GEP. This is the one we're going to focus on mostly tonight. If by any chance everybody doesn't have it, here's a link where you can download Google Earth Pro. If anybody's interested, you can leave that up for a second, or you can just Google Earth Pro download. The other application is NASA's Whirlwind, which is an open source virtual globe API that can be downloaded right from whirlwind.arc.nasa.gov, and it functions pretty much the same way, but Google Earth seems to be the more popular, and that's what we're going to focus on. Two tools that are going to be most important to us are the ruler option and the elevation profile option. So this is a chunk right out of the Magli chapter. The tools an archaeoastronomer needs to use in Google Earth are simple. The ruler option, which allows the calculation of distance and azimuth between two fixed points. So if you look across the top, the red arrow at the top is pointing to the ruler tool. This is where we can click that and our ruler tool will pop out. If you look 3 spaces there to the to the left, you'll see like a clock. But that icon is one that I don't have called out, but we're gonna mention it a little bit later. And then number 2 is the elevation profile option, which is accessed from the edit dropdown. This is going to only be available once you have your line drawn between 2 points. Once the 2 points are determined and you draw your line between the two with the ruler tool and then save it, then your line will turn from yellow to red, and you will have this option to access the elevation profile. And it says here, which visualizes the elevation between two extrema of a chosen path, and thus the projection of the line between the 2 points previously selected. So the ruler gives us what we're going to call for now the azimuth. We're going to come back and maybe re-examine that term of our desired direction for the main axis of town, sides of buildings, and things like that. The elevation profile will allow us to deduce the horizon height from a fixed observation point. So these 2 points we're going to use in an example here from the temples of a site called Silanunte. These are referenced in the brief pages by Magli, and we're gonna look at what he really just throws in as images and brief captions, but we're gonna dig into it a little bit deeper. The temple here is at 37 degrees, 35 minutes north. That's going to be our key point, our latitude. And this is actually Temple E of a group of temples. This one is in the best shape out of the still standing buildings. So just as a brief introduction, I mean, we're all familiar with this, but I figured I'd throw it in here. There's, half a dozen different celestial coordinate systems. We're interested in 2 primarily, the horizon coordinate system and the equatorial coordinate system. The equatorial system, that's the information that we need, but it's much harder to gather in the field. So the horizon coordinate system is what we measure, and then we use spherical geometry to get from one to the other. So basically, what we want in the end is our astronomical declination, which is going to define a point on the horizon that we're pointing at. So to do that, we need a couple points of data. We need our azimuth. So we can measure that in the field by measuring the bearings from magnetic north and then applying the magnetic declination to correct this from magnetic north to true north or polar azimuth. Or we can measure directly using sun sighting techniques with our theodolite. Or number 3, what we're going to look at tonight is the use of tools within the virtual globe software. The other point of data that we're going to need is the measure of the horizon altitude, which we can pick up with either a clinometer or theodolite total station, or again with the tools that we're going to look at tonight in the virtual globe software. We need our latitude, and we can pull that from a GPS receiver or obviously again from Google Earth. And then once we have all these, well, really these 3 pieces of data, we plug them into this equation to get our declination, which will be the arc sine of the sine of our latitude, the sine of our altitude, plus cosine of our latitude times the cosine of our altitude times the cosine of our azimuth. And then finally, once we have our astronomical declination, we can use that in an ephemeris to determine where, determine what day the sun rises at our declination on the horizon. I can just pause for any questions or comments at this point.
Quick suggestion, Chris, or a tip if people don't know the coordinates that you gave in Google Earth. The quick way you can put them in is just, you don't have to put in the degrees and the minutes and the seconds. You can just use spaces.
Mm-hmm.
So for example, what Chris just said, it'd be 37 space, 35 space, 11.58. And then you need to end, and then you separate it by a comma, and then it's 12 space, 50 space, 06 E for east. And then the Google Earth will go right there.
Right. Yeah, thanks.
Do you need anything for pain?
Not at the moment.
Okay. I brought you in this machine. Dr. Caskey wants you to have it. Have you used one of these before?
I have. Chris.
Yep. We'll just give him a second. Okay. So with that, let's jump into our example. Here we have Temple E, Escalante, and you can see the line that we've drawn from our inner chamber of the temple, from the back through a sighting on the front end of the temple, and we've extended that out. The line that I have here is 95.19 degrees. Again, you'll see it as recording as heading. We're gonna call this our azimuth, and you can see that it actually aligns pretty well to a modern road that's built at this site. Here you can see some of the other temples, the remains. That's, you know, as I mentioned, Temple E is in much better shape than some of the other temples surrounding it. But this is our ruler tool, you know. So when we looked at our screen earlier and we had the arrow pointing up to the ruler, once you click that ruler, this will pop up. You'll have the option then to set your starting point. You set it, you click it, and then you click your other extreme point, and then once you have your 2 points, your heading information will show up here in degrees. Again, we also have our latitude on every image that we have. So we have 2 of the 3 points right here that we're going to need to determine our astronomical declination.
Chris, can I ask a quick question?
Sure.
So on this one, it looks like you're not looking straight down at the temple. You've got some sort of a more of an altitude view.
That's right.
When you did the line, were you looking straight down at the temple? Or?
To get that nadir view that you're talking about, like from directly, that can be pretty difficult. This one here, this was about as good as I could get it at this angle, but we will kind of circle back and address that a little bit.
Okay.
So the next thing what we did here is I took that same heading that we had and pulled it back on a much larger scale from Escalante Temple E, and this is in the Isle of Sicily, by the way. It's a Greek temple, but built in on the Isle of Sicily. So from this point, the temple you can't really see, but 14 miles away we have this peak that can be seen from the temple. It's called Mount Fronio, several miles away. If we follow that line through the site, through the front center of the temple, through the, you know, from the back chamber, through the sighting, through the, you know, what's left there. This is what we see on our horizon, the bump of the peak of Mount Fronio. So here, if you see, we have our line that was yellow but then once we clicked it and went to red, we were able to hit our edit button, which brought down, remember, the drop down from edit, and then we were able to click the elevation profile. And at that point, it pops out this window right here, which shows us our endpoints. Now you can move this arrow back and forth. I have the arrow here at the very end just to get our elevation at 814 feet, but I could slide this arrow anywhere along the line and actually get the height that I'm looking for.
I'm missing how you get to the edit function. I don't know why. It's not happening.
Okay, so the first thing you need to do is pull up your ruler tool, and then you make the line between 2 points, really. Your best practice is to start where you would be as the viewer, and then draw your line out to, in this case, it's to the peak of Mount Cronio. It could also be done along the side of the wall, which, you know, is probably better for most of us. I'm just following the example that, you know, Magdi laid out in the reading. Just digging into his example a little bit deeper. But we'll see some other applications of it that might make a little more sense. But the key is you have to have your starting point and then your ending point. And then once you have your line, it's yellow, you click save, and then your yellow line will turn red. Once you have the red line established, then you can just go up to the edit button, and then it should drop down. Let me just page up a little. Once your line is red, you can hit edit. You'll see, and then down towards the bottom, it'll say show elevation profile. Right here. You with me?
Mhm.
Yep.
Okay, so this is our height in feet, which doesn't really tell us much, right? Because we're looking for a horizon altitude, which is it's an angle in degrees. So what we want to do, one of the options we have is we could just use our geometry and our trigonometric functions and say that we have our opposite, have our adjacent angle, and we can solve for, you know, the tangent of our angle. And in this case, we have an altitude of 0.630. So now we have our 3 points, altitude of 0.630, we have our azimuth of 95.18, and we have our latitude. One other thing, if you don't want to go through this math, this isn't quite as accurate, we'll see, but there's a really good program out there called Hey What's That, where you can obtain your own pretty low resolution profiles, but it's a free tool. You go in and you go to the site and you go to new panorama and you put in your latitude, your longitude, and you name you name your panorama, and it'll just generate one in a minute or two. And then you can move your cursor around. My red arrow isn't really accurate there. I see now that it's blown up, but where the brown line intersects at azimuth 95, I had my cursor right there at the top of the line. It showed it as 0.5. So this is obviously a coarser way to find some of the same information. You can see here that we're off by 1/10 of a degree. So that could end up making a big difference. But we have this free tool in our toolbox as well if we want to use it.
Chris,
Yes.
didn't the WhatsApp also generate a view shield of what's visible of the horizon versus a linear elevation chart?
I
Or
think
is there
it
a way
might.
to do that? Because I've seen that.
Yeah, I think it might. And I can get back to you. This is the only way that I've really used it.
Right.
I was introduced to this by Fabio Silva. It's
Right.
a tool that he used it, and for me, a lot of the stuff I do in Central America, I can't see the horizon, right? I'm surrounded by trees, and I don't have any permission or authority to remove the trees. So
What?
I'm sorry.
I was just kidding. I said, what? You don't have permission to remove the trees?
No,
No, but I think that, in that situation where you can't see the horizon, that if it generates a view shield from your point of observation, that would certainly be helpful.
Yes, it does. We played with that a little bit when we were out at Wallace the other day in the evening, and there's a top view that shows you what you will be able to see from that point.
Right.
So
Okay. Yeah. The view shield on it, right?
Yeah.
Is that in that WhatsApp?
yes.
So
Okay.
Hey, what's that? Yeah.
This is Rick.
I have a comment, Chris.
sure.
There's another program called Horizon, which I know Chris knows about. Horizon will generate the same sort of profile that we're looking at here on this slide, but at a much better resolution, without all the little squared off terrace looking features. And also at the same time, it will give you a panoramic sort of view, much like, but much better than what you're seeing with Hey What's That app. The problem with Horizon is that it's a bit intricate and involved to download it and to get it operating. But once you have it operating, it's a really a good program, and probably will give you more information about view sheds as well as horizon altitudes than Hey What's That. But I've used both equally.
Yeah, I 100% agree. But that very complexity is the reason that I just thought we'd do our detour into Hey What's That.
Yeah.
So
It's not very much fun to get it going, but once you have it, it's probably worth the effort.
Yeah. So when I was putting this together, I started playing with it to get it going, and I threw my arms in the air and said, you know what, I'm running out of time. I'm going to do Hey What's That.
So is that just www.horizon.com or what? What's the specific name on that?
It's complicated. Yeah.
Yeah. The best way to find it is actually the designer's name,
Right.
which slips my mind.
Isn't it Andy? Is it Andrew Smith?
It's something like that.
Something
Yeah.
like that. Yeah.
Yeah, just Google search Horizon Archaeoastronomy Andrew Smith, and you'll find it.
Yep. And it's a free download as well. But
Okay.
But yeah, setting it up is, yeah, I couldn't figure it out, frankly.
So once you find the program on the internet, you'll really need to download the user manual. There's
Right,
a PDF user manual.
yep. And it's like 175 pages.
Yeah.
It's pretty extensive, and it jumps around. It's not going to walk you through exactly what steps you need in their order to get this thing functioning. But after a couple of hours, you'll get it. It's a good program though.
Okay. Yeah, it's definitely the best out there, but this could have just as easily turned into a Horizon talk at that point, which maybe would be a good one for somebody. But anyway, so here we do have our course altitude. Horizons would have got us better one. Our math has got us one that's a little bit different that we're going to use. So here, if we plug in the variables that we've used, our sine of our latitude, I put it in decimal 0.63 I used for our altitude, and 95.18 I used for our azimuth, came up with a declination of -3.717, which is, again, looking at the peak of Mount Fronio. And then if we take that information, we can compare it to, let me move this bar out of the way so I can kind of see. Once we have our astronomical declination, we can use an ephemeris to determine what day the sun rises at that point of declination. So I used the JPL horizon systems here that Rick introduced me to. This ephemeris was created specifically, the one that we're going to show, by entering the dates that we're looking at. We're looking at the sun, and we're looking at our observer location of 38.58 east, roughly 12.8 north longitude. So the temple was built around 627 BC. So I used the ephemeris. I put in the start time of January 1st of 630 BC and the stop time of 627, December 31st BC. So we're right around there in the right range. And then I went to the custom settings and I took only the equatorial coordinates, because there's a lot more here that we can look at, but for our purposes, we only want to look at what day the sun rises at that declination. So get your data in here in the correct format, and then you can click generate ephemeris. Get back in here, and then it'll kick out a table. This is obviously chopped and shortened so we can get it all on one screen. But at our declination, roughly, we have two dates in the year where the sun will rise over that peak. The first is in the springtime, February 9th, and then again in the fall, September 3rd. So this mountain peak that it's looking at is kind of associated with Hercules or Heracles. The Greek temples at Sicily all orient towards the east, or rising sun on the east. But the dates in particular, they're not clustered around anything like the equinoxes or things like that. So the statistical analysis is still kind of not fully understood yet what these dates might be. They could be festival dates dedicated to Heracles or things like that. It certainly requires more study, but it gives us an idea of what was going on if we're looking at the astronomy in relationship to the orientation of the mountain. Any questions at that point? Kind of start to finish of the example.
I think it makes sense.
What's that?
I said it makes sense.
Okay, so we're gonna move on from Magli and his example, and we're going to look at notes on the accuracy of Google Earth Pro heading information for archaeoastronomy and landscape archaeology studies. As I stated earlier, this is by William F. Romaine in the most recent edition of Journal of Skyscape Archaeology. And this article is public access. That's accurate, right? This one is public, I think. Well, you have it anyway.
What?
So one of the first important points that this paper makes is that what we're actually looking at in reality are headings, because we're looking at a global or a virtual globe, which means that any line that we draw is in fact going to be an arc of a great circle. So since we're on an arc of a great circle, any point along that circle, we might change our direction, that we're facing. So these images show the angle between point B and its line of longitude, and then along that same great circle, point C has a much bigger angle between the line that's generated and its line of longitude. So these angles are still expressed in degrees, and as mentioned, it changes as we move along the larger arc of the Great Circle. So azimuth, of course, what we're more accustomed to dealing with refers to any angle between 0, which would be true north, and 360 degrees. It's also expressed in degrees, and it indicates a point on the horizontal plane. So just as we did in our example, what we're looking for is a point on the horizon, our azimuth, which we pair with our horizon altitude. So Google Earth Pro plotted lines are great circles again, and they're not straight lines. And they depend upon one's position on the line. So technically they are headings and they are not azimuths. On the smaller scales that we're going to be dealing with in any work that we do, which really includes the lines of sight, for argument's sake, we can use them as azimuths, but it's good to keep in mind that in actuality, they really are headings. So a heading, or for argument's sake, azimuth accuracy, depends on several different factors in the virtual globe software. It depends on relief displacement. One of the things that you brought up, Rick, camera tilt, georeferencing, spatial resolution, and any user-related variables that are introduced, like our zoom level, the computer screen resolution, and really just how good the user is at drawing the line, really. The accuracy of the line in question, it's going to vary from user to user. So one of those things, spatial resolution, the paper talks a little bit more than some of these other points. For archaeoastronomy, spatial resolution is the central concern. To take a measurement, the JP ruler needs to lock onto a pixel at both ends of the line drawn by the user. That's our yellow line that we draw. And once we say that, recall, it turns red, and then we can check out its profile. Spatial resolution is image dependent. And the other thing is these images in Google Earth, they do not tell us what their spatial resolution is. So every image has a different spatial resolution, and this affects the accuracy of the measured heading. So another definition here of the ground sample distance is the smallest spatial unit on the ground that the sensor can measure. And it equals the pixel size times the AGL, which is above ground level, divided by the focal length. And in practice, it's the length on the ground of one side of a pixel. That's our GSD. So the smaller the GSD covered by the pixel, the greater the resolution and the closer the match to the locations the user wishes to use as start and end points. So, and that makes sense, right? So a good rule of thumb is to take the image that you're looking at. If you're interested in finding the spatial resolution, you can compare it to a photo that you have where you know the resolution, and you can kind of gauge it that way. There's also other measures in there, using automobiles. If you can see the windshield, or if you can see, the sides of the, the bracer that holds it in. If you different things on the car will give you an idea of what the spatial resolution is, and that's a good thing to go back and read if that's something that you're interested in getting a better understanding of. So the accuracy of the GEP heading line is a function of the spatial resolution of the image and the length of the plot of the line.
Chris?
Yep.
So one thing that you don't want to do is take measurements using Google Earth Pro images from different years and think that you have the error is an average of those different spatial resolutions, which I've seen done in print in the Journal of Skyscape Archaeology. Problem with that is when you average those values, you're averaging spatial resolutions from older images that may be worse than a lot worse than the more modern images that you have. And so you end up diluting your own data and downgrading it. So select what you think is the best image. Make sure that the tilt and the tilt is set properly so that you're getting an accurate measurement, and then don't average a bunch of older images along with it, because it's not going to improve your initial numbers.
Okay, thanks. Okay, so Google Earth Pro, kind of as Bill was just talking about, produces an orthorectified image produced by calculating the nadir view of each pixel from various images, which are stitched together using automated photogrammetry. So Bill, with what you were just talking about, how does the orthorectification process kind of compensate for some of that, or just will it not?
No, the orthorectification process doesn't really compensate. If you have a Google image from 2023, the spatial resolution on that image probably be better than something that was taken in 1963. So if you have a measurement of 125 meters using the more recent image, and you have a measurement of 120 meters using the older image, what you do not want to do is combine those two and average them and think that you have now a better sense for the length of that line that you just drew, because you averaged two different numbers. The fact is, you're actually downgrading your initial 2023 better resolution value. So that's what I meant. Now, it doesn't really have much to do with orthorectification, although, I mean, it's all interrelated, and you're going to have better orthorectified images the more recent with the more recent Google Earth Pro images. By the way, I found the website address for that Horizon program that we had been talking about. So after we're done, if you want it, I'll read it off to you.
Yeah, we can drop it in the chat.
Yeah, I just dropped that in the chat down the bottom.
I don't know if I know how to do that.
Okay, so like what we were just talking about, though possibly the newest image may not be the best image. So a lot of times we'll see that if you go back maybe a year or two, for the particular site that you're at, there may be a better resolution resolution for the image. So when I talked earlier about the ruler, if you recall, I said the icon that was 3 to the left that looked like a clock. That's the that's the show historical images icon, and you can click that, and a slider will come up where you can actually go back in time and pick, different, different view. So we have multiple sources here. Some of the older ones, some of the older Landsats, of course, aren't going to have as good a resolution. But if you slide back and forth, you can pretty much find for where you're at what's going to be the best. All right, so let's talk about the methodology in this paper. So the whole purpose of this paper is to assess the accuracy of the GEP measurement tool for header information. So what it did was it compared the heading data to heading information that was retrieved from airport runway documentation. The airport runway documentation has high standards for safety reasons and other reasons, so they have very accurate ground truth runway headings, which are recorded in the documentation. And this test was run against 3 different airports, and we're going to look at how they worked. So the first one was Chicago O'Hare, and the measured heading from the documentation corrected for the magnetic declination is 270 degrees. And that's what showed up on the GEP measured heading. So also the paper talks a little bit about an inverse Vicente calculator, ARGS 2022, that uses a different method for calculating the heading, and that came up to the same measurement. Anything you want to add about the Vicente calculator? Because that's kind of new information for me.
I'm not sure if your slide updated, Chris.
Oh, what are we? Okay, I'm
Satellite.
sorry. I'm
Just
sorry.
on
What
the
are
satellite,
you seeing?
The
Satellite.
sources.
What do you see now?
Same image.
Still the satellite.
What does it say?
It's the Google. You're talking about Google Earth 4 and the sources of the imagery, and then at the
Oh,
bottom,
really? Okay. Sorry about that. Let me see. I'll stop sharing.
maybe relaunch it or.
Yeah, let me start to share again. So can you see you can see my screen now, right?
Yeah.
That
So
one.
let me,
Yeah. No, I didn't get that one. Yeah.
so where are we at now? Can you see the methodology?
Right.
Yep.
Right. Yep.
Okay, great. So just to recap, the airports have really good documentation, really good runway headings documented in their plans. And this is a test of Google Earth Pro heading against these airports. So now you guys can see Chicago O'Hare, right?
Yes.
Okay, great. So the measured heading, 273.8, corrected for magnetic declination. So the magnetic declination of any location can be picked up from the NOAA website. If you go out and just Google NOAA and magnetic declination, will take you there, and you can just put in your location and your time, and they'll spit out the corrections you need to make from magnetic bearing. So once corrected, we have a measured heading of 207 degrees, and we have our ruler tool showing the line here represented in yellow on the runway, with our 2 control points actually here's our point of our view, and here's our end point, which gives us our 270 degree, which matches exactly our corrected heading. And as I mentioned before, the inverse Vicente calculator value is also 270 degrees. So we have a pretty accurate match here. So moving on to the Cairo International Airport, we have a measured heading of 46.2, corrected with its magnetic declination to be 49.2. And the line along the runway here in yellow with our 2 control points measures to 49.11. It's just off a little, but if you look at the value produced by the AGRS 2022 calculator, that gives us a 49.117, which is nicely between our 0.11 and our rounded up 0.2. And the third airport that was the test was run against was the Hong Kong International Airport, with a corrected heading after magnetic declination of 250.9. The Vicente inverse calculator calculated the azimuth at 250.92, and GEP measured the heading at 250.87, which rounds up to 250.9 if we're only looking at one significant digit.
Yeah, Chris, that Vicente calculator is a really helpful tool. I think I gave a website address in the article, but if you are in a situation where you're not certain that Google Earth Pro is accurate, and there are areas of the world where it's not quite as accurate as you'd want to see, use the inverse Vicente calculator. And what that does is it takes latitude and longitude coordinates for your control points and calculates the azimuth between those 2 latitude longitude points. Very, very useful and precise. And it's based on, well, it's based on the WGS 84 standard. So it's pretty reliable and pretty helpful.
Thanks. So after the test of these airports,
What's that?
I said I was just moving on. After the test of these airports, the paper then goes into use case studies of actual archaeological sites. A couple of them are from the Ohio River Valley, where much of Williams' work is done. The Egyptian pyramids, but for our benefit and for our group and in the the time we have, I focused here on the case study that he used on Pueblo Bonito, Chaco Canyon. This orientation actually was the subject of our very first journal club, and it's been visited a couple times since. So if you recall, based on Andy Monroe's PhD work and work he's done with Kim Malville at the Great Houses in Chaco Canyon, they did theodolite studies, and here's 2 photos from Andy's dissertation of this measured wall from both the looking east and looking west, and it measures along just about 270 degrees at 270.2 degrees, making almost a perfect east-west line. So if we click on the house, the wall, so this is, I went into Google Earth to just get a cleaner image. You can see my control point down here, and the endpoint I chose down here. And I came up with the same result as in the paper of 270.23. Again, the points made in the paper that we already know what that is, so we can kind of cheat until we get the number that we're expecting. But if you're careful enough, you're going to get the right number anyway. So one other point that I want to make, this azimuth here, if you recall some of the earlier papers about archaeoastronomy at Pueblo Bonito, recognized the north-south and the east-west attribute of this, and the fact that this guy is not aligned at 270, but has a 86-degree azimuth, and it was suggested that this aligned to the rising sun of the equinox. So I just took this a little bit further and drew our line out there at 86 degrees as far as we could go. I got my horizon altitude from, hey, what's that? We had our converted latitude decimal, and used this information to generate the ephemeris, and found that we can corroborate the work of Monroe and Malville, who were able to show photographically that this line did not align with the equinox. We can see here that the sunrise dates correspond to this declination that's calculated of 7.016, or actually March and August, and do not line up with the equinox. These guys went out early in the morning with a camera to prove it didn't, but we could have done it this way as well. Which brings me to my last slide. This is a photo Greg took from their work at Escalante Pueblo. So we plan on using a Google Earth workshop to complement some of the groundwork that the society is doing at Pueblo, Escalante, and Wallace, and some other sites, and integrate with the general membership what's actually going on, with ground truthing and photogrammetry and surveys at these other sites, to integrate things that we can all contribute into the greater cultural landscape project that the society is working on. So one of the things the workshop will aim to do is, you can see the alignment of this wall points out to this peak on the horizon. So one of the things we'll do in the workshop is we'll measure that azimuth. We'll get our horizon altitude and our latitude, and we'll calculate the declination of that and see what day of the year the sun rises above that peak, and other things around the area, to try to complement the work on the ground. And that's my last slide. So I'm gonna open it up to the floor. See if there's any questions, any other comments.
I had a comment, Chris. I do a lot of Earth observation, and you had definitely mentioned it, but the poise of the satellite for anything with relief, right? So a wall is going to have an angle associated with it based on the angle of the image. So whenever possible, going to the base.
Right.
The base is the best way to go, and then shadows can be your friend. You can really get a sense of the object, and then it's casting a shadow. It'll take you right to the base of it.
Yeah. Another good trick is you can zoom in to set your control point, your first control point. And then what I do on, my laptop is a touchscreen. So I know if I move my mouse, it'll move the other end for the control point, but I can use my fingers on the screen actually to navigate without changing my line. So if I set my first control point, and then use my fingers to zoom out, or maybe use the plus minus slider with my finger and move out, then I'm still free to move my second control point out. And that way I have a good solid first control point, at least from really close up.
Yeah. And I think before you save the line, you can go and move the different positions.
You can, yes.
Yeah. But once you save, it's locked in.
Once you save it, it's locked in. And another good thing to remember is you don't have access to the elevation profile until you save it.
Right.
Oh,
And that was my next question on the elevation profile. So we talked about the error on any given satellite image for the orthorectification.
Mhm.
How does that, I guess there's error on the orthorectification, but then there's also that elevation comes from a DEM or something, right? So there's going to be positional error on that. So we're kind of combining those two things.
No.
No? Okay.
No. There's horizontal position error with GEP as well as GPS. However, with GEP, with Google Earth, the horizontal accuracy, let's say, is not crucial to your measurement because you're comparing relative points. So if one control point is in error by a certain value, then the corresponding control point, if it's properly orthorectified, should also be off from the actual position by the same amount. So we're talking about relative positions, not geo-referenced locked to the ground positions. Does that make sense?
I think so. I I just,
Yeah.
the general question, I wasn't sure, because when you get your DEM, it's, XYZ data, and there's some error there. And then we have the satellite image orthorectified, that's another XY data. And so they don't necessarily have to be the same, say an XY error.
And that's why when I do these calculations, I double check and I go to the inverse Vincenti formula, which uses longitude, because that is locked to the WGS 84 grid. So I haven't really found that to be an issue though. So
Yeah, I haven't either. I'm just curious.
Yeah.
So it's two different data sets. So
Yeah, and I think the thought behind Chris's question is the paper deals with the accuracy of headings or the azimuth. What is the accuracy of the data that we can use to help gather for our horizon altitude?
over horizon accuracy. So I'm not hearing this very well. So in answer to that question, there are issues with the elevation data for Google Earth as well as all of these horizon programs. Because the shuttle radar is not as accurate as we would like it to be, particularly in mountainous areas. But out where you guys are in the Southwest, it'll be should be relatively accurate. But I think the worst is about 16 meters that it can be off the elevation data, which is pretty significant for mountainous areas. Yeah. Did I hear that question right?
Yeah, I think it was actually in regards to the way I took the data from the elevation profile and used it in a geometry equation to calculate horizon altitude. I think that's what you were talking about, Chris, right?
yeah, and that was just a general comment on actually discussion point of that accuracy. So.
Yeah. I mean,
so there's another workaround. There's another workaround. You can take a program like Terrain Navigator Pro, which is basically a USGS topographic map, but it's also built on aerial photographs. Anyway, get the elevation data from that and use that to make the trigonometry calculations. And I think you're gonna find that it's basically a wash, you know.
Okay.
And I guess one of the things that has come up before we've discussed is what level of accuracy in these kinds of measurements is culturally necessary. You know, what is culturally significant?
Yeah, I'm reminded of a statement Rick made recently of how surprised he was in the field that your theodolite measurements were to actual measurements done on the Sunto compass and clinometer. And be that as it may, I mean, these results seem to be a lot more accurate than anything we could get from.
Oh, sure. Yeah. And that can be done remotely most of all.
Exactly.
The other thing we discovered, because I kind of changed my attitude about it, the first time we were out there, we were using kind of just rudimentary compasses, like, I guess I'm going to say your $40 to $60 compasses. And we were coming out with just wild differences. You know, just whoever was using it was the degrees off. And this time we went out and just one-on-one, we compared transit. So, obviously a device that is going to be very, very accurate. And Chris was out there with a Sun2 compass, and we were within about a third of a degree all the way around. You know, basically did the entire horizon, every point. And so I kind of changed my mind about that a little bit. And then what we kind of came to is be very handy if you have a theodolite, or in my case, it's a regular just transit. It would be very handy to just have a fairly accurate compass with you, just to double check, because there is just error in counting or moving or twisting. And in our recent experience, we were out at Wallace, and I'm comparing all my notes, and I said, one of these lines is 20 degrees off. One of them has to be. I just wrote it down wrong, or I measured it wrong, or didn't see it right. And we went back and remeasured and of course corrected for the problem. But it was, after the fact, you have to just go back and say, does all of this make sense? And the more you can do this little sort of make sense corrections and just double checking yourself along the way, I think it's really, really helpful. So at least that's what we discovered. One more thing, I'm going to go back kind of towards the beginning. Is you remember we were talking about, hey, what's that app, and Viewshed? And so I also, in the recent work we did, I have access to really some very sophisticated ArcGIS software through my university. And it's wacko expensive. So we haven't been really sort of, trying to rely on it, especially for our membership. But I compared specifically the Hey, what's that Viewshed with the ArcGIS Viewshed. And it was, again, remarkably accurate. And so showed certainly enough level of detail that I got a very good sense of what was in the foreground, what was in the background, and all that.
Oh, that's good to know.
Part of our analysis, yeah. So, and it's probably it's likely getting better all the time, just because somebody's paying attention to it. I think they're probably working with it every day, making it even better and better as they go. In the case of the Haywoods app, I just one more comment is they round everything to a degree. And that kind of makes me a little crazy because, obviously nothing is going to be exactly on a degree. So when they round it for you, it's
and hey, what you mean?
Yeah. So if you do, so what we were doing is in advance of our field work.
I think they rounded to a half a degree, right?
No, everything I saw was rounded to just a degree. I never.
Do you mean azimuth or?
Right.
Yeah, azimuth.
Okay, I was thinking altitude. Okay.
So and it's not bad, and for our purposes, it's not bad. But in my frame of reference, I think about 10 minutes, which would be about I think that's probably where I'm sort of aiming my accuracy for. And if that app is initially just giving you locations that we're now then going out and finding and using as our reference locations, if they're rounding to a nearest degree, it's a bit of an issue. So we can have that conversation later.
Okay, that looks like it's about it then, I guess, so.
Yeah, I don't have anything else.
Well, I just want to say, William, I really appreciated the paper. I think these tools are amazing, but especially in our community, people grab them and run with them, and it's good to take a moment and make sure they actually do what they say they do.
Yeah, thank you very, very much for showing up tonight. Appreciate it.
For joining us, too. Thank you for your membership.
Yes, thank you, Chris. Thumbs up, Chris.
All right, guys. So hopefully, next month we'll have a workshop put together where we can put some of this into practice with the cultural landscape project that you guys are heading out, and pull some more of the membership in to get their hands digitally dirty.
Right. All right.
Great presentation, Chris. I have one question for William. Is he still there?
I'm still here. I'm
Yes,
having
William.
trouble. I'm having trouble understanding and hearing most of the conversations, but I can hear you okay.
Okay,
ahead.
well, I was this is kind of off the topic, but I was in Ohio about a week and a half ago, and I stopped at Hopewell and Serpent Mound, and they were telling me that at some of the Hopewell Mound complexes downstream, I guess, from the national park thing, that there are several sites that have wood hinges. Are you familiar with any of those?
Well, there's one site in particular that that seems to have a wood hinge, and that's the Hopewell site itself in Ross County. There may be also another one or two at the Fort Ancient site, which is further to the southwest.
Right.
I think those are about
They
the
said
only
the Mound
ones that-
City.
Let's
They
see.
said Mound City, the Hopewell Mound City had one, and then something that started with an S. I've got it written down somewhere. So
Right.
okay,
Site Mound.
yeah,
Site Earthworks.
yeah,
Yeah.
that's about right. Yeah.
Well,
Okay.
I don't know about Mound City having any sort of wood hinge. I do know that some post holes were found, I believe, in along a section of wall at the Hopeton earthwork, which is just a little bit south of Mound City. So, yeah, those wood hinges
Okay.
are, they're far and few between, but they are there.
Well, I know the one at Cahokia has somewhat become, problematic as to whether, it really existed or not. So
Oh,
I'm just kind of curious.
I don't think there's much doubt that it existed. The question is, why would you have so many posts if you're talking about an equinox alignment, maybe a winter and a summer solstice rise alignments? Then what's the purpose of all of the other posts that form the three or so circles? That's
Right.
that's the issue. I've actually photographed the equinox sunrise at Cahokia, and it's spot on. It's right on.
Right.
Yeah. So what about those other posts, though? That's the question.
Right. Well, that's certainly up in the air.
Yep.
So. All right. Good job, Chris. I look forward to the workshop.
Yeah. Everybody needs to make sure they download Google Earth Pro before we do. You might want to put
Got it.
some stuff out in the early announcements about that.
Yeah.
Well, all right, everybody. Thanks for joining.
Did you stop?
Well, I don't know if you can hear me. I just was wondering, we'll miss the next one because we'll be in Namibia.
Oh.
And I know nothing about the archaeoastronomy of Southern Africa. And I wondered if any of you could give me any references before I go, as even if we're obviously studying the San rock art there, but we'll be in quite few places.
1 sec. Can you hold 1 second?
Sure.
Where'd you get this? Where'd you get this? Where'd you get this? Where'd you get that?
Sorry, this is taking me so long.
When are you going?
June the 14th, we leave.
Wow.
So we still have some time. So if you want to just email me, I think I'm on the list, ebillo@aol.com. I have a whole bookcase full of archaeoastronomy references, but I must admit I hadn't yet researched it. I'm still trying to do a bunch of other stuff
That's a big trip.
unrelated to the travel. So
All right.
So you say you will be documenting rock art there like you normally do?
well,
Or-
actually, no, well, yes, in that we'll be taking the higher resolution photography, and we'll if there's places that can benefit from 3D modeling, we'll be taking enough pictures to do that. And we're not bringing our drone, so we can't do mapping or anything. But this was not the focus of this trip. It was sort of more of one of our very first international trips many, many years ago was to Namibia. And actually was for the first IFRAO Rock Art Conference. It was when it was first starting. And so this particular 2-week trip goes to about half of the sites we went to before and has added on another, sites we haven't been to. So we're looking forward to seeing new and also going to see old friends and see how our interest is also in conservation and how they have weathered over time. So we have our own goals, but it's not actual official documentation with the paperwork, all that I normally would do with the site here in the USA.
Okay.
I dropped a bibliography that I put together on African archaeoastronomy into the chat.
Oh,
It's broken into sections. At least it'll be a starting point for you if you find them, and then you can go into those papers, bibliographies. Obviously, the rabbit hole.
it would be really fun if I did find something. So thank you very much.
Certainly.
And obviously, if we see anything, we'll let you know when we get back.
Yeah, that would
Yes,
be
great.
great.
Thanks again. We have to leave
Okay.
now.
Okay, Chris, I'll see you next time.
All
Get
right,
that
thanks,
downloaded.
guys.
Everybody, appreciate it.